Hi, I'm Yiping Jing. Today I'm going to talk about my project this semester. It's about robust transceiver design with autoencoder. So first is the introduction. Current wireless communication systems, like in 6G, we're trying to adopt for a higher throughput design to increase the efficiency of our communication system. So this brought significant attention to holographic multiple input, multiple output system. And this HMIMO system employs a larger scale surface to enhance signal coverage and better resource utilization. But using this system will also increase the complexity for our communication system, like when estimating the communication channels we're having, we will introduce some various sources of estimation errors. So our work here is to aim to design a robust recoder design for this HMIMO system in the presence of imperfect CSI. So let's first talk about how we design our precoder in flat-faded, like traditional MIMO system. So in the traditional system, we can formulate our channels like this, and we want to design a precoder F by maximizing the channel rate, which is on equation 2. So if we try to expand the SNR representation using the notations we have, we can rewrite our signal power like this. And if we further assume our signal to be unit power, and we introduce this notation Q to equal to F times F Hermitian transpose, we can rewrite our signal power like this. So what we want to do is we want to maximize this. So we know that the channel capacity can be maximized when Q can diagonalize this whole term inside. So assuming we have a perfect channel estimate and we can have the single value decomposition of the channel, we know that we want to design our precoder as F equal to the V component here in the SVD. So this is under the assumption that we have a perfect channel estimate. But the motivation is that we are trying to adapt for a new cell-free practical HMIMO system, and this will introduce some various sources of estimation error, such as mutual coupling, because in HMIMO system, we increase the density of antenna elements. So now these antennas are really close to each other. So now we are like these two components will interact with each other. So now we're corrupting the ideal independent channel assumptions here. So this will introduce some channel estimation error when doing the channel estimation. And the second one is polarization diversity. Because in HMIMO, we're considering signals coming from various directions. So this will increase the density we will have to estimate like throughout every different angles. So these increased multiple polarization components will increase the estimation error. And the last one is about the near field effects. Because in HMIMO, we want to further increase the efficiency for every user receiver we're trying to design. So this will require us to have a more precise distance. And because we assume that the users or the antennas, the distance can be really close. So the traditional assumption about far field effects will no longer be applicable in here. So these interactions have to be accounted for, as they can affect the channel estimation process by altering the propagation characteristics. And also we want to directly optimize a more practical objective using ergodic rate. So by taking account of the channel statistics, the metric can better capture the achievable performance under practical conditions. Now I'm going to talk about our problem formulations. So we're now considering a channel estimate with error. So we reformulate our channel estimate like this, where H hat is the original channel, like the real channel we're having now, and the delta H here is the linear error we have in our channel estimation. So we assume the error is not too bad and is within some ellipsoid mismatch like this. And we also adopt an autoencoder structure to allow this robust design for the precoder. So the F component here now is changed to a nonlinear structure here. So we call it phi. So our whole system can now be written like this. So the signal power we have derived have to do a little bit modification because we introduced some new notations. So if we expand all these, we will arrive at equation 16 here. So if we introduce a notation gamma equal to this term, and thus we can rewrite our signal power as equation 17. So because we now have a random channel, so we cannot directly do the SVD component to maximize our channel capacity anymore, because the channel now is no longer deterministic and we cannot perform an SVD on a random channel because we have a random unknown estimation error within some constraint. But our goal is still the same, that we want to maximize the rate under some transmit power constraints, like formulated in here. So to accommodate this mismatch, we want to rewrite our objective as to maximize the minimum rate under some channel mismatch delta H, and with the power constraint here. So we cannot directly deal with it with the usual, like directly expand with convex optimization techniques, because the constraint, first we can see like in here, the delta H is within some region. So this will introduce infinitely many constraints for delta H. So we cannot directly expand it with Lagrangian because you cannot formulate out infinitely many constraints in it. And the second term is, the second problem is we have a maximizing minimizing problem here now. So to tackle down this, our method is, first we expand the maximum problem with an auxiliary variable t. So now we transform the maximum problem into one maximization problem with some minimization constraints here. And the second step is to solve this transform minimization problem and directly expand it with Lagrangian dual problem. So now the problem looks like this. We transform the first minimization term here into this equation 21. But notice this one is still not a convex problem because R here contains a log function, and log is a concave function, but inside log, its argument with respect to delta H is making the curvature of the objective intermediate. And so we tackle down this problem with, first we use quadratic transform from fractional programming to expand the problem into a convex function with auxiliary variables. And then we bound this whole problem objective with the first order linear expansion of it, and then we solve the optimal mismatch delta H here with majorization minimization techniques. So now we have the optimal delta H here that will minimize the rate of the whole channel. And so now we can rewrite the original maximum problem as equation 22. So we can now deal with this problem with Lagrangian function, and by solving the gradient of the Lagrangian, we can have the following iterative update steps for each variables with some notation is specific like this. And notice that because we're introducing a nonlinear component in here, so this gradient can be solved with the classic gradient descent. So finally, we can conclude our overall algorithm as here. So our goal is try to find an optimal set of parameters theta in our autoencoder so that it will maximize the rate. So first we initialize the parameters theta randomly, and then also for the Lagrangian dual variables, we initialize them as some random value greater than or equal to 0. So the steps will be, first we obtain our optimal delta H channel mismatch using the proposed MM algorithm above, like we just talked about. And then we iteratively update these parameters using the equation we just talked about earlier. And then we do this until the rates converge to optimum maximum. So this proposed robust recoder design framework, assuming an imperfect channel estimation, which is a common challenge inside the new HMIMO system we try to consider with. So by adopting projective transform and majorization minimization techniques, we are able to transform a problem into an iterative optimization problem like we just saw. And the solution can mitigate the impact of channel estimation errors and maximize the minimum rate of the system. And we expect to, by incorporating autoencoder structure, we can allow the nonlinear components in the optimization, and we hope that it can bring us a better performance. And we are still implementing these simulation overall, so there's not yet for a result to write out, but this is my presentation today. Thank you.